we have discussed logistic regression as one of the problems where my response variable is not normal and hence we cannot use the usual linear regression theory. So we discussed it as a special case of generalized linear models where we create a link function such that the transformed value of the response can now be more or less approximated by a normal distribution and hence it can be modeled as a linear function of the regressors. So in the logistic setup, we saw that the response was binary, that is coming from Bernoulli distribution, and hence it caused some problems. One more such case where there are problems is count data. Okay, so if my response is count data, then first there is a problem that okay, I cannot approximate a discrete distribution directly by a continuous distribution unless I have a very large n. That is one issue. But it is not just that. The thing is Poisson distribution. So if I feel that the count data can be adequately modeled via Poisson distribution, then there is a further trouble. Because in the Poisson distribution, we know that expectation of x is same as variance of x. So if I have my response variable as Poisson, that is, if I have my yi as say Poisson with some mean mu I, because we know that the mean has to depend on the corresponding regressor value, so mu has to be function of I, then variance of yi will also become mu I, which means that variance of yi is also function of the regressor values. Basically variance of yi changes with I. So this is a violation of our linear regression assumption that we have constant variance. Okay. Hence, we need to use some link functions to handle the Poisson data as well. Now, what is the link function requirement here? Just like in the Bernoulli setup, we wanted our expected value to lie between 0 and 1. Here, we want our expected value to lie between 0 to infinity. So, we want it to be positive. So, if I want my expected value to be positive, then what can I do? Then I could perhaps define a link function in such a way that, so I can define eta I as say log of yi. Okay, so if I model this eta I, so if I take log link function, then eta I becomes beta naught plus beta 1 x1i, sorry, xi1 in our linear regression terminology, beta 2 xi2 plus beta k xik, okay, plus epsilon. We model this. Then, does it satisfy my requirement? What will be my yi hat? My yi hat will be e raised to eta I, and e raised to eta I will always be positive irrespective of whatever the values of betas or xij's are. Correct? So log link function is one of the best link functions that one can use while dealing with Poisson regression. Okay. So, and how does the estimation take place? Just like in the logistic setup, we can go for maximum likelihood equation because we know that the distribution is now Poisson. That is our assumption. So, I can write my likelihood as product over I going from 1 to n e raised to minus mu I raised to yi upon yi factorial. Correct? Where what is my mu I? Mu I is the expected value. Okay, so here we are going to take mu I as e raised to beta naught plus beta 1 x1i plus beta k x ik. Okay, so if I compute log likelihood, what do I get? I will get log L as summation I going from 1 to n minus mu I plus yi log mu I, and that y factorial I can keep aside as a constant because anyway when I differentiate it will vanish. Okay, so this becomes summation I going from 1 to n minus mu I is this, that is minus e raised to beta naught plus summation beta j x I j plus yi times log mu I is the linear function. So beta naught plus summation beta j x I j. Okay. And now this I have to differentiate with respect to individual betas. Again, as you can see, this is not a linear function of betas, so differentiating it is going to be complicated. We are not going to get explicit solutions, but we again use iterative procedures. Okay, we can use the same procedure, that is iteratively reweighted least squares, to get estimates of betas. Once I get estimates of betas, I again follow the same inference procedure that we discussed in the logistic regression setup. That is, we can use the deviance statistic again. Deviance will be defined in the similar manner, log likelihood of the saturated model minus log likelihood of this model. So we can use the deviance. Okay. How do I get the log likelihood of the saturated model? So in the Bernoulli setup, we saw that. So in the Poisson setup, what I'll do, for every xi, I should have its own estimate of mu I. For every distinct value of xi, I should have its own estimate of mu I. That is the saturated model. So what we will do, if my data is something like this, that is x is 1.5, 1.5, suppose I'm sorting my data in the increasing order of x. Okay. And if I have this, etc., and the corresponding values are suppose y1, y2, y3, y4, y5, y6, y7, then for x equal to 1.5, my estimate of mu, so mu corresponding to x equal to 1.5, mu hat will be y1 plus y2 by 2. Mu hat corresponding to x equal to 2 will be y3 plus y4 plus y5 by 3. And if I don't have repeated observation, then I take that value of y itself as the estimate. I don't need to take average. Okay. So this will give me deviance of the saturated model, substituting these mu i's. Then I'll compute the deviance of the current model, and then we again use the differences in the deviance for inference. Of course, we can also use the second derivative of the log likelihood trick to get estimates of the variance of the betas. So basically the entire inference goes in a similar manner to what we discussed for the logistic regression model. Okay. The only difference is, for the link function, instead of using the logit link, we use log link. Okay. And log link ensures that my estimates of the the predicted value of yi's are always positive. Okay. So let me stop here. Thank you.